I'm Josna Devi Bodapati, Assistant Professor, Department of CSE, Indiana University. In this lecture, I'll talk about what is the best way to split the data into train and test sets, and also what are the different cross-validation techniques that are available and when to use which type of technique. We'll discuss that in this lecture. So let us see what is the train, validation and test data for the given data set. So any given data set, we usually divide that into training, validation and test data sets. So training data set is the one on which we implement the model. That is, the model is trained on this data set. So such the data is called as training data set. So here the model learns its parameters using this training data. For example, in case of the neural networks, all the weights and biases of the model are decided depending on the data set that is available during the training. So that is what the training data set is. You execute the model is tuned to the data that is available in the training set. So that is, it is biased towards this data set. The goal is to make the model more generalizable. That means our model should work on the data that is not seen during the training. So to use the separate portions of the data called validation data set and the test data set. So validation data set is a small portion of the data set that is usually to fine tune the hyperparameters of the model. So once the model is trained, we test the model on the validation data set. So if the accuracy is good, so then we test the accuracy of the model on the test data. These are tuned so that the model's performance is improved. So validation data set is never shown to the model. That is, during the training, this data set is not used. It's also called as development set. So here, I mean, data set means a portion of the data. So it is completely trained on the trained data set. Then if it is doing good on the validation data set, then we check the model's ability on the test data. This is called as the unseen data. The data is never shown even for the evaluating of the performance. It's not like the validation data also. So it's never shown to the model. The model is tuned, actually the model is trained on the training data, and for the parameter tuning, we can use this as the evaluation data set, that is the validation data set. So finally the model performance is reported on the test data set. So this is how the data set is divided into three splits usually: training data set, validation set and the test sets. So let us see different cross validation strategies. So what is cross validation? So it is a technique that involves reserving a portion of the data set. So why we should have such a reserved portion of the data set is because this is how we measure the effectiveness of the model. Always when we implement the model, it should be more generalizable. That means when we implement the model, it is usually trained on a set of data. So if we check the performance of the model on the trained data, then its performance would be high because the model is already tuned to that trained samples. So it is not a good way to measure the performance of a model on the training set. That is why we had to use a separate set that is not shown during the training of the model, and such a data set is required to gauge the effectiveness of the model. Strategy is called as cross-validation strategy. So how do we validate our model? So we use that strategy. That's why it's called as cross-validation strategy. There are various methods available for performing this cross-validation. So the most popular ones are validation set approach, then leave one out cross-validation strategy. So we usually shortly call it as LOVCV. Then the KFold cross-validation, which is a generalization of this leave one out cross-validation. Then the other one is a stratified KFold cross-validation. So these are the different strategies we can use for cross-validation. Let us see the validation set strategy. Most of the data sets like IMDb or MS COCO, such standard data sets, they provide separate standard splits. It's like this portion you can use for the trained data, this portion you can use for validation, and this portion we can use for test. So usually the standard data sets, they provide separate splits. If such a split is not available, randomly we shuffle the data and then we can split the data into separate splits. Like we can follow 80-20. That means 80% of the data is used for training and 20% of the data can be used for testing. Or otherwise we can follow the 70-30 or 60-40 rule also. So depending on the data set, we can use the any of these splits. So in case of the 60-40 split, so 60% of the data is used for training, whereas 40% of the data is used for testing. So a portion of this data set, the 40% of the data set here, or the 30% here, or the 20% over here. So this separate portion of the data set, we are reserving it for gauging the performance of the model, and such a portion of the data set is called as holdout set. So we call it as test set or the holdout set, full length original data set. So in that we are splitting the data set into two parts. So either you can follow the 80-20 or 70-30 or 60-40. So even we can follow 85-15 also. So that is up to us. Then in the training data itself, training set itself, we can partition that again into two halves. Again, two portions. Again, so that is up to us. So in that 80, if we consider that 80 as 100, we can use it as something like 90-10 or 85-15 rule. So while splitting the validation set. Then once we split the data set into three portions. So training set, validation set, and the test set. As I already mentioned in the previous slide. So training set is the set of examples or the portion of the data on which we implement the model. That is, the model is trained exactly on this set of data. Whereas the validation set is a set of examples on which you evaluate your model while training. So this validation set is a portion of the examples. Those are reserved to check the performance of the model, but only during the training itself. So that means your hyperparameters can be tuned depending on the performance of your model on the validation set. So if you observe here, so the model is implemented, then we are training it. So once the model is trained, so our predictive model is ready. So then when the predictive model is ready, we apply the validation set and test the performance of this model. So if we are comfortable with the performance of this model, then so we stop the training. Otherwise, we again tune the parameters, that is change the weights or change the hyperparameters. So then we again implement the model, that is train the model on the training set. Again we apply the model on the validation set. So to implement to check the performance of the model. So like this in a cyclic fashion. So this will be repeated till we get a model with which our performance is acceptable on the validation set. So once we get a model with a reasonable accuracy on the validation set, then we test the performance of the model on the test set, and that becomes the performance of our model, and we report the model on the test set. So this is how we can actually use the reserved portion of the data set to validate our model. So this is how we do in the validation set strategy case. So let us have a look at the other strategies. So next strategy is a leave one out cross validation strategy. So in this leave one out cross validation strategy, so what happens is, let us see first of all why should we go for this leave one out cross validation strategy rather than using the validation set strategy. So in the validation set strategy, what we are doing is we are reserving a portion of the data set for the testing, that is a model performance evaluation. But when the data set is very small, it is not possible to split the data into training, validation, and the test set. So when we do that, our test set will be very small. So to avoid that, what we do is, so we evaluate our model on each and every sample of our model when our data set is very small. What we do here is, let us consider our data set is having some 1 to n number of samples. Then first we reserve the first sample and apply our model, train our model on the examples from 2 to n. Then we use this, the first sample as a test sample, and then we get the performance of the model. Then similarly, we reserve the second sample, and then on other samples, we train the model and test the performance of the model on the second sample. And we repeat this for every sample. So here we are leaving one sample out, and we are testing the performance of the model on the sample that is left out. So that is why it's called as leave one out cross validation. And the average performance of all these models is given as the performance of the whole model. So in this way, your model will not be biased towards a specific portion of the data set. So the bias of the model will be very less when compared to the validation set strategy model. So here there is a problem when the model is trained. If you have n number of examples, your model has to be trained or implemented for n number of times. That is, the model should be trained for n number of times, so which requires huge amounts of execution time. The model is trained for n number of times. So avoiding this, there is another strategy that is introduced called as leave one group out cross validation strategy. So in this case, instead of having one sample for the cross validation, so we have a group of samples. So first here in this case, so the first group, this group we consider it for testing, and the remaining part we consider it for training. Remember, the validation set again can be taken as a split from this train data itself. And in the second iteration, we take the second group of samples, another group of samples, and the remaining portion. So this set of examples, including this set of examples, all these examples. So except this group of the marked examples, the rest of the examples will become the training data. In the iteration 3, again, the next group of samples in the line will become the test data, and the rest of the examples will be the training data. So this is how we repeat this process for certain number of iterations, that is till the last group is reached for the test set. So the average performance over all these iterations will become the performance of our model. The advantage of using this leave one group out validation rather than using leave one sample out cross validation is, so there the model is executed for n number of times, which is computationally heavy. Here the model is executed for k number of times. The computationally it is less expensive than the previous strategy. Now we'll see the next strategy called as KFold cross validation. So when the data set that is a given data set do not follow any standard splits, it is very useful to use the KFold cross validation strategy. So there's a most popular approach, widely accepted approach to follow the KFold cross validation strategy. So in this strategy, what we do is, so entire data set is first split into K-folds. So here, so this is the entire data set. So this is the testing. So one portion of the data set is considered as a test set. Actually, it is divided into number of portions. Say for example, 10 splits. So the entire data set is split into, say for example, 10 splits or the K splits. So now one split of the data, entire data, will act as a test data, or we can call it as a holdout set also. And the remaining 9 portions, or the K minus 1 portions, will become the training samples. So the model is first implemented on this train data, that is the K minus 1 splits, and on the kth split, the model is tested. So in the next iteration, so we'll take the other split. So instead of taking this split, so we consider this split as a test split. And on the K minus 1 splits, we apply the training. And this will be repeated for K number of times if there are K splits. That is, till we reach the last split, that is this split for the testing, we repeat this process. And the average performance of all these K folds will become the cross validation performance of the model. And this is what is called as the K-fold cross-validation strategy. So in this case, when we use the validation set strategy, so we are using only one split for the testing and the remaining for the training. But here, instead of doing that, the model will not be biased in this case towards a set of examples. The model performance is evaluated on the entire data set. So this is how the modal bias would be very low when compared to the validation set strategy. So consider this picture which shows the K-fold cross-validation strategy. Say for example, we are taking K folds, fold 1 to fold K. So in the iteration 1, so the fold 1 will become the test set, and the remaining, so second fold to the remaining kth fold will become, that is the K minus 1 folds becomes the training data. And in the second iteration, fold 2 becomes the test set, and the remaining folds become the training data. That is, the model is implemented or trained on all these splits. So on and so forth, it is repeated for all the K iterations. And the performance of the model in each iteration is computed. So on the first iteration, the performance of the model is evaluated on the fold 1, the second iteration on fold 2, in the third iteration on fold 3, and so on and so forth in the kth iteration on fold K. So this is how it is repeated for K number of times, and the model performance is the average performance of all these folds. So that is how it is evaluated, the K-fold cross-validation strategy. So the second one is the next strategy is the stratified cross-validation strategy. So this is very, very important when the data set is very, very imbalanced. Consider this data set this data set is having two classes. One is a female class and the other one is a male class. The male class examples and the female class examples. So in the data set we have taken the female test samples. The female data samples are very, very low compared to the male samples. So in the stratified cross-validation, so what happens is each fold, here also we follow the same strategy of the K-fold cross-validation, so except a few alterations. So when we apply stratified cross-validation, so the model ensures that each fold is a good representative of the entire data set. So before applying this, so what happens is the data set is completely shuffled, so that it will not be like only a specific portion of the data is used. So it will be shuffled randomly. Random shuffling happens so that the data samples in the data set are mixed together, and then we get one good representation of the whole data set in each of the folds. And one more thing is here, if we observe, so in each fold, so here this is the first iteration. So this fold, so it's a 5-fold cross-validation actually. So in the first iteration, this is the first iteration. So in the first iteration, so the first fold contains, so actually our original data set contains, assume that 20% of the samples belonging to the females and 80% of the samples are belonging to males. So same will be ensured in each fold also. It will not be like a fold contains all the male samples and the other fold contains only the female samples. So it will not happen. So that might happen in case of the K-fold cross-validation. But in stratified cross-validation, that will not happen. So what we do here is, so the proportion of the samples in each class in each fold is in proportion to the samples in the original data set. So say for example in the classification, if we consider the classification problem, so each fold contains approximately equal percent of samples from each of the class. So here we have taken binary class. The same can be extended to multiple classes also. So if it is in this case of the prediction problems, that is the regression problems, so the mean response value of each fold is ensured to be equal. So this is how a stratified cross-validation strategy is helpful to get a good representative of the whole data set in each of the folds.